All right, let's get started. This is the third and final deep learning lecture of the course. And this lecture is on deep generative models. So we'll explore a few different families of models that are parameterized using deep neural networks. So let's talk about generative models very broadly first. We might consider approaching a data set which has a certain number of data examples. Each data example has a certain number of features. And we have this large matrix here. And we might consider plotting them. If we have 3 features where we can actually just visualize them directly, we could imagine plotting each data example in this space. And we might continue. And what we'd end up with is the empirical data distribution. So this is the set of points in our data set plotted out in this space. And what we mean by generative modeling is generally density estimation. So we want to look at our empirical data distribution and actually estimate a probability density to associate with the space. So we see that in regions where there's a lot of data examples, we have a high density, whereas in regions with not many data examples at all, we have a much lower density. And a generative model, as we said, is just a model of the data, or a model of the density of the data distribution. So why would we want to actually learn this model? Why would we want to estimate the density of our data? Well, one thing we can do is we can take our model and now generate new examples from this density. So we can generate new samples that resemble the data. So we can just take this model and start sampling points. And now we have these new points that we've sampled that hopefully resemble the data, but we have this nice procedure for doing this automatically. And recently, we've been able to do this with things like images, where you have these very high-resolution images that we can generate that look almost indistinguishable from natural images, and yet these images are totally generated by models. We can do very similar things for speech data, where we can generate, like the voice on Google Assistant is generated by a model. You can do very similar things with speech. Similarly, you can automatically generate music. And there's been even experiments showing you can simulate particle physics experiments using deep generative models. So there's really a large range of things you can do when you're simulating this data. Another area where people like to think about simulating data is in reinforcement learning, where maybe you want to learn a model of what environment you're interacting with, and then actually be able to generate new experiences using that model instead of having to actually interact with the real environment. So hopefully you can reduce the sample complexity of your interactions by learning this model automatically. Another reason we might want to use a generative model is to actually be able to automatically learn some structure about our data. So if we have this set of data points here, where we have these 2 features, we might imagine learning a generative model that estimates the density within these regions and finds that actually there's these 2 kind of clusters of our data. And then now if I give you some labeled examples, one from each cluster, you can automatically kind of generalize in some sense and say, well, OK, I saw one example from here, and now I can imagine that the rest of this cluster is probably also associated with that label. So you can hopefully generalize to new tasks much easier. And people have been showing similar kinds of things where you can extract structure from data in this automatic way by, for instance, taking this data set of small 2D shapes and showing that you can actually extract meaningful latent representations where you have one vector or one dimension in your latent representation that's encoding the vertical position, another dimension that's encoding the horizontal position, others that are encoding things like the size and the rotation. You can do similar things with extracting structure from natural images, where you have things like color, or actually which digit you're looking at, or similar things with faces. People have even looked at extracting structure from speech data, where you can extract male versus female type of identifiers, and also looking at more like 3D representations of shapes as well. So to actually model data distribution, let's consider this probability of P data of X, where X is our data. We also are going to have our model, which is parameterized by some parameters theta. And we might consider this space here in one dimension with X versus the probability. And so we have this data distribution in green. We sample some points from that. This is us gathering data examples from the real world. And then what we'd like to do is fit a model to these data examples that we have shown here in pinkish purple. And the main technique for going about doing this is maximum likelihood estimation. You've probably seen it throughout this course, but the idea is to fit a model that assigns the maximum likelihood to the observed data. So this is generally thought of as thinking about actually a KL divergence between the data distribution and your model's distribution. And what you like to do is minimize this KL divergence and actually bring these two distributions together. But as we'll see, you can rewrite this as this difference of logs. And really, you can't change the parameters of your model to somehow change the data. So really, you can only just optimize this log probability under your model. So what we have here is the expectation under the data distribution of the log probability of those data examples under our model. And we can think of this as averaging over a discrete set of data that we have and just evaluating the log probability under our model of each data example and then averaging that. And like with supervised or discriminative tasks, there's also a bias variance trade-off in generative modeling, where you could imagine having a very simple model that just assigns a very simple distribution to your entire data set, or perhaps you have a much more complicated model that tries to model every single exact data example very precisely. So there's a range of model complexities you can have, where with low model complexity, you're generally going to have a large bias, and with large model complexity, you're going to have a large variance. So a deep generative model is a generative model that uses deep networks to parameterize some of these probability distributions. So that's the only conceptual leap, is just throw a deep network in the mix and you have a deep generative model. And today we're going to talk about 4 different families of deep generative models that have become quite popular in the last 5 or so years. There are a lot of other models. This is a field with a lot of history that goes back much before deep learning became popular. But these are the main families that we're going to look at and discuss today. So let's jump right in with autoregressive models. So I've given each model a little graphic here. And this graphic is generally representing the main conceptual idea you should kind of think about when thinking of that type of model. And so hopefully this will become clear in a moment. So conditional probability distributions. I could give you the sequence, this morning I woke up at, and you could probably think of what word would come next in that sequence. So what you're doing is you're imagining that you have this set of inputs that you've been given, which is x1 this, x2 morning, and so on and so forth. And then you want to assign a probability distribution over this next entry, x7. So conditioned on all of the past, what is the next item that might appear? And so you could actually imagine drawing out a probability distribution like this, where probably I would say something like 8, 7, or 9. But maybe I would also use a word like dawn, or I woke up at home. But I very almost no chance I would say something like encyclopedia. It's essentially a 0 probability that I would say this morning I woke up at encyclopedia. So you can imagine there's kind of differing degrees of probability for each of these words, and we'd like to form a model that actually tries to take advantage of this property. So we consider a data example here, which consists of a certain number of dimensions, and those dimensions are these features, and we'll consider the joint probability distribution over each of these features. And what we can use is the chain rule of probability, which is this very general, very basic rule. Hopefully you've seen it before when dealing with probability and statistics, but we'll just go through it really quickly. So we're going to split the joint distribution over all of these features into a product of conditional distributions. So what we'll do is actually use the definition of conditional probability to split up this joint distribution here. We have this simple example with A and B into P of A given B and P of B. And we're going to recursively apply this to this joint distribution over all of these features. And so we can write, well, actually we have just P of x1 and then P of everything else given x1. And then we'll just keep applying this until we have P of x1, P of x2 given x1, all the way up to P of xm given everything before xm. So we've just broken up this joint distribution into a product of all of these conditional distributions. And generally, you can write it in this type of form. And even though I've gone through it in this kind of sequential order, and often it makes sense to consider, if you have a sequence to consider in the sequential order, you can write this for any order. Any conditioning order is a valid way of splitting up a joint distribution. So we're going to model the conditional distributions of the data by auto-regressing to each value. Now, what does that actually mean? We have all of our m features here in our data example, and now we're going to assign a distribution over the first feature. We're going to have P of x1, and this is our model's distribution. And now what we're going to do is actually feed that first sample into our model, and we're going to have now P of x2 given x1. So we'll generate a distribution on the next dimension. And we'll continue this on to the third dimension and the fourth. And you get the idea. And we'll continue this all the way through until we reach the final dimension. Now, we talked about maximum likelihood estimation. How does that apply in this context? So again, we had this idea of we want to find the parameters of our model that assign maximum likelihood to the observed data examples. And we thought of this in terms of an average log probability. Now, we saw that the log probability for a data example under an autoregressive model could be factorized as a product of conditional distributions. And the log of a product, you can just turn that into a sum of those logs. And so now we have this expression for the log probability of a data example. And we plug that in to our entire expression for the maximum likelihood estimate. And now we have these sums over both data examples and over dimensions. So what this actually means is that we're going to go through and sample data examples from our data set, and then we're going to run our model on those data examples, evaluating the probability of each dimension as we go through, and then sum the entire result up. So how might we think about parameterizing these conditional distributions? One idea would be to use a recurrent neural network. So this seems like a pretty obvious idea. We saw that recurrent neural networks, they take in a sequence of inputs. They have this hidden state that they're maintaining. And so you could imagine having this very nice automatic way of constructing these probability distributions. And so for any given conditional distribution, for here I've shown P of x5 given everything less than x5. We have x1 through x4 that are fed into the model at each time step. And then at the next time step, we're going to spit out a distribution over the next dimension that we might imagine seeing. So there's examples of this. Andrei Karpathy had a nice blog post about this. And then there's things like pixel recurrent neural networks that are actually trying to model images using recurrent neural networks in this way. So you're autoregressing each dimension using a recurrent network of an image, even though an image is 2D. But we might also consider using a convolutional neural network to perform this type of autoregression. So here I've drawn a convolutional network that takes in 3 inputs for the size of its window, does some computation, and then spits out a distribution over the next dimension. So here we've considered P of x5 given x2 through 4, and that's doing this kind of convolution sliding across this sequence of inputs. So we could use either a recurrent network or a convolutional network. And people have shown, in models like Pixel CNN, you can actually perform this type of autoregression as well using convolutional neural networks on images. But a really pretty cool application of this was in Wavenet, which is this generative model of audio. And in here, you're using a convolutional neural network over sequences of audio input. And importantly, to get a larger window over the past to condition on more variables, essentially, you use these dilated convolutions. So you're kind of looking back further and further with each successive convolution here. And so these models like Wavenet have been shown to actually be very, very powerful and useful for modeling audio sequences. And Google almost immediately started using this in their voice assistant. The sound quality was just phenomenal. So we didn't actually touch on how we might actually have this output distribution, what form that might take. So just to go over it very briefly, if we had discrete variables we were dealing with, we would probably want to assign some type of categorical output or like a Bernoulli distribution on a binary variable. Whereas if we're dealing with continuous values, say it's some amplitude in our speech waveform, then we might want to assign a Gaussian distribution or a logistic distribution or something else. So you can use either discrete variables or continuous variables with this type of modeling approach. And so we kind of talked about it previously, but when you're actually trying to generate a new sample from this model, you're going to be autoregressively feeding in each sample back into the model here. So here what we've done is we've said we have P of x1, which is this distribution over the first dimension. We're going to feed that into our model, even though it's the model's sample and not the data example. And then we'll generate the distribution over the next dimension and then sample from that, feed that into our model. And so we're kind of feeding the model back into itself in this way to generate a new data example here. And so let's do some thinking for 1 second. We have this training procedure that we talked about where you have now each data example being fed into the model. And then we have this sampling procedure where you're feeding the output of the model back into itself. And take like a few seconds to think like, what issues might arise if we're sampling from the model? What could happen? What would be some issues we might run into? Yes?
Because you're putting like the distribution of your outputs, like of the sampling and the inputs during training might not be the same, and so your model might be really good at like predicting the output given like ground truth, but it's not good at predicting good outputs given its own outputs.
Exactly. So the general idea is just that we might have errors in our model distribution, and if we're feeding our model samples back into our model, those errors might compound over time steps. And so this might lead to poor samples in the long run. And so one technique people use is what's called teacher forcing, where during training you're actually feeding sometimes the model's own samples back into itself. And there's not, I wouldn't say a great justification for doing this other than it helps to somehow regularize the model and generate more plausible samples when you're actually trying to sample it at sampling time. So some example applications where people have used these types of autoregressive models are in things like text completion, image modeling. So this is the pixel RNN where you feed in half of an image and then have it generate what the rest of the image could look like. And so you see for different samplings, you're going to have different outputs where here you have the top part of a dog, and you can see there's different bottom halves of dogs that are generated and things like that. And then as we talked about, speech is a great application as well. And so very recently, people have been looking at even a different form of autoregressive model called a transformer. And these types of models have become very, very popular for modeling text data. And so just a few weeks ago, OpenAI released a new, well, they didn't release the model. They publicized a new model called GPT-2, which stands for Generative Pre-training 2. And this top part of this prompt here was written by a human. So the top part, if you can't read it, says, a train carriage containing controlled nuclear materials was stolen in Cincinnati today. Its whereabouts are unknown. And that's the conditioning that goes into this input. This is the first few dimensions that are fed into the model. And then the rest of the text here is entirely generated by the model. Conditioning only on those past generated words is generating a plausible continuation of this sequence. And so I'll just very briefly start reading this. The incident occurred in the downtown train line, which runs from Covington and Ashland stations. In an email to Ohio news outlets, the U.S. Department of Energy said it's working with the Federal Railroad Administration to find the thief. The theft of this nuclear material will have significant negative consequences on public and environmental health, our workforce, and the economy of our nation, said Tom Hicks, the U.S. Energy Secretary, in a statement. Our top priority is to secure the theft and ensure it doesn't happen again. So, at least to me, this sounds entirely plausible. Like this is a perfectly constructed English document. And so part of OpenAI's reason in not actually releasing the model was that they felt that this model was so good that if they released it, people would be able to generate fake news at an alarming rate. And so at the very end, we'll touch very briefly on how there's some ethical concerns that are now starting to be raised over how good these generative models are and how that might impact society in negative ways. So the next family of latent variable models that we're going to talk about are called explicit latent variable models. Sorry, the next family of deep generative models. And so these models, again, here's the little graphic that I've made to help you think about what these models are actually doing. They have some latent variables here, which are generating some observed variables. Let's go through a very simple example. So imagine we have, again, our data distribution here plotted in one dimension, and we have some probability measured along the y-axis. So the first approach might be to say, let's not even use anything fancy. Let's just fit a very simple distribution to the data. And here we just fit a Gaussian to the entire data set. So we have a Gaussian distribution that we've adjusted the mean and the variance of this Gaussian distribution to just maximize the likelihood under this distribution of the data examples. And now we might consider a separate approach where we're actually going to use a latent variable to model the data distribution as well. So what we've done here is instead of just having a simple distribution over x, we now have a joint distribution over x and a latent variable z. And again, using the chain rule of probability, we can break this out into probability of our observed variable x given z, and then some prior distribution over z. And we might consider that conditional distribution to be a Gaussian distribution, but the prior over z could be a Bernoulli distribution. So we could have some coin that we flip in this latent space, and then each outcome of the coin flipping would generate a different distribution. And so here what we have is a problem where we have to actually get what would be the probability distribution over x. And what we can do is actually marginalize or sum over all of the values of z. So in order to evaluate what is the probability of any given data example, we sum over all possible values of z to get our probability x. And what that amounts to is a kind of weighted mixture of different distributions here. So we have two mixture components here in this case. And in the graph, you can see that now you'd have these two Gaussian distributions that you could model this distribution with. And hopefully this performs much better. So probabilistic graphical models is just a framework for thinking about modeling relationships between random variables. So we'll go through some notation really briefly, just because I think it's helpful to be exposed to this. You have observed variables, which are represented with these shaded circles, and you have these unobserved or latent variables that are represented with these empty circles. And you can have directed connections, which signify conditional probability distributions, and you can have undirected connections, which signify these kind of clicks over random variables. So we won't talk about undirected random variables or undirected graphs, but people are starting to look back at these types of models. And then to denote a set of variables, we have this plate that goes around the variable itself, and usually denote how many of those you'd have. So if we have n data examples, that would be represented with this plate with n. So let's put our thinking caps on again and think about, we saw autoregressive distributions before. How might we think about modeling an autoregressive distribution with plate notation? So consider if you have three random variables, what type of connections might we have in this type of plate notation? You could have that, exactly, or you could have the alternative mapping as well. So we'd have arrows actually between the data dimensions, like we said, and these are going to be modeling things like you have some initial distribution over x1, and then you have this conditional distribution on x2 given x1, and likewise a conditional distribution on x3 given x1 and x2. And these are all modeled with some parameters theta. So in comparing an autoregressive distribution here with a latent variable model, we see that we actually have now taken all these relationships between the observed variables and put them into a latent variable. So now Z is modeling all of these relationships and then mapping down to each variable individually here. So we have similar types of distributions being modeled, but in very different ways. So let's consider what's called a directed latent variable model. And in this case, we have, again, this generation where we have a joint distribution over x and z, and that's given by this conditional distribution of x given z, and then our prior distribution over z. So this is the joint distribution that's generated as a product of the conditional likelihood and the prior. So in order to actually generate from this model, what we're going to do is sample from our prior, and then use our samples from the prior to give us samples from p of x given z, our conditional likelihood. So an intuitive way of thinking about this is that you might have some graphics engine where the latent variables would be what objects are being represented, what is the lighting, what is the background, and then you have this renderer which is generating all sorts of natural images or that you might imagine seeing. So in these latent variable models, one thing we often are concerned with is posterior inference. And what that means is that we want to evaluate what is the probability of our latent variable z, given that we've observed some observation x. And so we can use definition of conditional probability to rewrite this as the ratio of the joint distribution to the marginal likelihood. So this x down here, this is our usual thing we think about when we have our likelihood. We call this the marginal likelihood because we've had to marginalize over z. And we can use Bayes' rule to evaluate this. And so an intuitive example of this would be that we have this observation of cat, and then we want to say, given these pixels that we have, what is the probability distribution that we're observing a cat now? And so we have this, you can just use Bayes' rule directly to say the probability distribution of cat given these pixels is these pixels given cat, probability that you would even see a cat in the first place, and the probability distribution that you would even, probability that you would even see these pixels in the first place. So to actually evaluate our model, to get this actual likelihood that we want to use to perform maximum likelihood inference or estimation, we need to actually marginalize over the joint distribution, over the latent variable. So we need to marginalize over all latent variables, which essentially amounts to considering all possible underlying latent states that the model could be in. So if we think of this cat observation again, we have to think, how likely is this observation under my model? So for every single possible setting of lighting, background, objects, everything, we have to consider every possible situation the world could be in. How likely is this observation? So as you can imagine, that might be very, very difficult if we have a complex model. So to actually try to perform maximum likelihood estimation, again, we have to sum over all of our latent variables to marginalize. And in practice, this is often intractable. And so you can't usually do this in practice, particularly if you have a deep network parameterizing some of these conditional distributions. It's essentially impossible. Yeah?
How well could you do using some sort of MCMC method where you sample from the latent space?
Yeah, so you can use MCMC methods, and you're performing this type of approximate inference where the more you sample, hopefully you do arrive at kind of the true posterior distribution. People have looked at using these, but in practice, they don't tend to be used very often, just because they tend to take a while. Versus what we'll talk about, which is variational inference, which is maybe a more crude approximation, but is much more efficient. So the main technique people use, at least these days, in in deep generative models is to use variational inference to try to overcome this issue with the marginalization just being intractable. So what we're going to actually do in a nutshell is just say we're going to lower bound the log likelihood by introducing an approximate posterior distribution. And we'll unpack what that means. So this approximate posterior distribution is this distribution Q that we come up with. We decide what form of distribution it's going to be. And this is going to try to approximate the true posterior of the model. And by introducing this distribution Q, I'll spare you a lot of the math, but the take-home message is that you can break up the log marginal likelihood into this term L here and the KL divergence between the approximate posterior and the true posterior. So now we've taken the quantity that we want to evaluate and split it out into these two terms here. And this quantity L is often called the evidence lower bound or the elbow, and that is expressed in this form. We'll unpack that in the next slide, but just think of this as this kind of functional here. And by observing that the KL divergence is always non-negative, so it's always greater than or equal to 0, that means that this term L here, the evidence lower bound, is a lower bound on the log marginal likelihood. So we can actually replace this log probability here, or we can replace in maximum likelihood estimation the log probability with the lower bound to hopefully do pretty well. And that's as captured in this algorithm called the variational expectation maximization algorithm. So the E step, what we're going to do is we're going to take our Q distribution, our approximate posterior, and fit it as close as we can to optimize the bound L of x here. So what that's going to be is maximizing this bound, try to make it as tight as possible, try to make it as tight as possible to the log marginal likelihood. And once we've done that, now we have this estimate of this lower bound. We're going to optimize the lower bound with respect to our parameters as we would in regular maximum likelihood estimation. And so this E step, because the actual log marginal likelihood does not depend on our approximate posterior, we're indirectly actually minimizing the KL divergence between the approximate posterior and the true posterior when we optimize this lower bound with respect to our approximate posterior. And so you can think of that as like you have this posterior distribution which is defined by our model for a particular data example. And this could be some complicated distribution. And now what we do is we introduce this simpler distribution, oftentimes this Q of z given x, and we're going to try to fit it as closely as possible to the true posterior, indirectly. So what is this evidence lower bound? So we wrote it in this form before, but you can actually split this out. So you split out the joint distribution, and then now write this splitting with a log, and then combining the prior and the approximate posterior, we can see that what we have here is actually a reconstruction term. So why do I say reconstruction? Because we want to say sampling the latent variables from our approximate posterior distribution, so this latent distribution that we're maintaining, we want to maximize the log probability of the data example we're actually observing. So given our latent representation, we want to maximize the probability of our example, while at the same time, we don't want to stray too far away from the prior that we have on our latent variables. So this is enforcing some type of regularization, preventing us from just assigning whatever distribution we want to try to fit the data as well as possible. So we have these two competing forces, and there's a lot of connections between this and compression and information theory and rate distortion theory and things like that. So there's kind of a whole deeper aspects to this as well. Let's think, though, going back to the variational EM algorithm, we might actually want to use a separate inference model to allow us to perform this E step much more efficiently. So this is kind of where deep learning has come into practice here. And the idea is that instead of actually directly optimizing our approximate posterior, we're going to have a separate model called an inference model, which is going to output this estimate of the approximate posterior for us. So we're going to feed our data example into this inference model. It's going to output or regress to this estimate of this distribution in latent space, which we'll sample from to try to reconstruct the data, and then we'll evaluate the KL divergence between these two distributions in latent space. And the idea behind what are called variational autoencoders is just that you can reparameterize the sampling of a Gaussian variable using this reparameterization trick that we talked about, I think, in the first deep learning lecture. So the idea is that instead of sampling z from a Gaussian distribution, you sample it using this deterministic function that includes this additional stochastic variable. So there's been a lot of things that have developed after the variational autoencoder, like using hierarchical latent variable models where you're extracting structure at different levels, and you have these types of more complicated inference schemes. Likewise, people have looked at sequential latent variable models where you now have a sequence of latent variables in latent space, and you can use that to model things like speech. And then my work has been looking at, instead of actually encoding data examples, using some type of error signal to update the latent estimate. And you can use this also in sequence modeling. So the next family of models that we'll talk about are called these invertible explicit latent variable models. So previously we talked about explicit latent variable models, and those models we saw, you can't actually perform exact maximum likelihood inference. You have to use variational inference or some other technique to approximate the marginal likelihood. These models actually allow you to exactly estimate the marginal likelihood or evaluate the marginal likelihood. And it's all based around this simple idea, which comes from the change of variables formula. And it's just using an invertible mapping to directly evaluate the log probability, log likelihood. So let's go through what is the change of variables formula. So let's talk about a simple example. Imagine I have this simple uniform distribution, which I'll call my base distribution, that's defined from 0 to 1. And it's a uniform distribution, so it has to integrate to 1. So I'm going to have a probability of 1 in this interval. And now what I'm going to do is actually apply a transform to this simple base distribution. And that's going to map it to this new variable x. And so what I'm going to do is apply this function, or this transform, to z, which is 2z plus 1. That's all I'm going to do. So I'm going to take a sample from pz. I'm going to apply this transform. I'm going to get out a value of x. And now I want to know, what is the distribution over x? So if I apply this transform, what distribution should I expect as a result? And you can motivate from the perspective of conservation of probability mass that the probability within an interval, the probability mass, should be conserved during this transformation. So in that way, we can actually directly evaluate the probability of some value x in our x distribution is equal to the probability in the z distribution, and then the absolute value of this derivative. So this is essentially just a scale factor that's saying when moving from this space to this other space, you have to scale by the derivative. And so this derivative might be positive, it might be negative, but what we're really concerned with is the actual mass itself. So we're going to take the absolute value of the derivative there. And so what we have is this type of setup where we have this simple distribution, this base distribution over this variable z, and we can apply this mapping f of z to get to x, but then we can also apply the inverse mapping to get back to z. So we have our base distribution, our transform distribution, which are defined by these mappings. And the change of variables formula in general terms says that the probability distribution of the transform space is equal to the probability distribution, probability in the base distribution times the absolute value of the determinant of the Jacobian of the inverse transform. So that's a lot to think about, but we'll try to motivate why that would be the case. And this you can write in log probability terms, just expanding things out. And so this form down here is actually the form that we tend to use in practice. So this Jacobian matrix here. So this is the Jacobian matrix of the inverse transform. So that's Jacobian matrix of this arrow down here. And so that's similar to the probability that we saw, or the the derivative that we saw in the previous slide. So we had this derivative dz dx. This is that derivative generalized to multiple dimensions. And in these multiple dimensions, you actually would have not just a single scalar derivative, but a Jacobian of derivatives. And so what we're going to do is evaluate the determinant of that. And you can think of the determinant as this local distortion in the space. So we have some volume of the base distribution. The determinant of the Jacobian of the inverse transform just tells us this is how the space expands when moving from one space to the other. And so what we can do is actually transform the data into a space that's easier to model. So we can have a simple distribution in our latent space, here a isotropic Gaussian, and we can apply this transform f of z to get down to this much more complicated space that could be modeling our data. And yet we could take data examples and use the inverse mapping to get back to the simple space and evaluate probabilities in this space rather than in the complicated space. So that's the main idea behind using change of variables formula for density estimation. And so we can actually exactly plug this into our maximum likelihood formulation, where now we have the log probability of our data example. It is expressed in this simpler distribution P of z, which we've gotten through this inverse mapping, and then essentially the amount of scaling we had to do to go from x to z. So this is saying we have some scaling that we need to account for, and then we have the actual probability in the simple space. And so we can just plug that directly into our formulation of maximum likelihood, and then essentially just evaluate that as it is. So in order to actually use the change of variables formula, we said we had to evaluate this determinant of this Jacobian. And so for an arbitrary n by n matrix, this is going to be worst case order of n cubed, which is not good if you have a large space. So in practice, what people will do is restrict the transforms to have either a diagonal or a triangular inverse Jacobian, in which case you can evaluate the determinant very easily as just the product of the diagonal entries. So it's just saying we need to restrict ourselves to fairly simple transforms in order to actually have this thing work out in a computationally efficient manner. And one very cool approach for doing this is what's called masked autoregressive flow, or MAF. So the intuition behind this comes from thinking about autoregressive sampling that we saw before as actually a form of transform. So we had xi here sampled from this distribution over xi, which is given some mean, which is a function of the past dimensions, and then a variance perhaps, which is also a function of the past dimensions. And we saw that, well, what we could actually do using the reparameterization trick is to express xi in terms of the mean and then the standard deviation multiplied against an element or a number that's distributed according to this random distribution, this standard Gaussian. So we've reparameterized the sampling procedure as this transform of a simpler base distribution. So it's a pretty cool insight to see this. And so in general, we would have to generate each of these xi's sequentially. And so we can think about actually applying the inverse transform. So just take this equation here, solve for zi, and now what we have is a form that can be parallelized in a very computationally efficient manner. So what does this actually look like? So the transform that's defined by masked autoregressive flow is of this form, where you have some base distribution over your z's, and you have some transform distribution over your x's. Now, in order to actually get the next dimension over x, what we need to do is have this function over past dimensions of x, and then we'll apply this transform using the current dimension of z. And then to get back to z, we would just apply the inverse operations to get that variable back. So let's put our thinking caps on yet again and think about what is the form of the Jacobian of this inverse transform. So we have, so this down here, this z equals x4 minus stuff. This is our inverse transform for the dimension 4 here. So can anybody think about like what would this Jacobian look like? Would it be diagonal? Would it be triangular? Would it be a full matrix of Jacobians? Any guesses?
Guessing triangular.
Triangular. Okay, we have a guess, triangular. Okay, that's correct. Good job. So what we actually have is a lower triangular structure here. So in this functional form, we see that zi depends on xi. So here we have z4, which depends both on x4, but it also depends on x1 through 3 in this formulation. So through these functions a and b here. So each zi, each dimension along this here, depends on only up to that dimension in the x's. Hopefully that makes sense. So this basically saying this variable here only depends on x1 through 4. It doesn't depend on anything past the diagonal. And so if we want to evaluate what is the determinant of this Jacobian, as we talked about, this is actually, for a triangular matrix, just the product of the diagonal entries. And so we can take this and evaluate what is the derivative of each of these individual transforms, and then just multiply those together. Oftentimes we'll be taking the absolute value in the log as well. Yeah?
Do you have to worry about z and x having different dimensionality in this case? So
in all of at least all of the current approaches, they always have the same dimensionality. So we always restrict it to be two continuous variables, and you have this invertible mapping in between them, so they have the same dimension.
So like if you were doing like an image or something like that, and you in like a GAN framework, you'd have like 100 latent variables. You couldn't do this.
Yeah, you could not do that in that framework. You would have to have the same number of latent variables as you have observed variables. Yeah. So this idea has also been applied to variational inference, like we talked about from before, where instead of having a simple approximate posterior distribution, you can start with a base distribution that's simple and then apply these transforms to get a much more complicated approximate posterior, which tends to actually give better performance in practice. And so this is another application that is also using similar types of mathematical frameworks to do this. And so some recent works that have looked at this. So this paper, NICE, is kind of the first paper that really demonstrated this approach in a large way, I would say, for deep learning. And then people have followed up on that with things for both variational inference and for direct density estimation. And more recently, these models have been able to scale up to much larger data dimensionalities, like natural images here with large images of faces. And the basic idea behind this paper, GLOW, which came out last year, was just to use one-by-one convolutions to parameterize these invertible mappings. But there's actually a really cool other application of this, which is for distilling an autoregressive model into a model that can be parameterized. So we talked about Wavenet from before, which is this autoregressive model that applies these convolutions across a sequence of audio inputs. And so actually sampling from that is very expensive because you have to imagine sampling each dimension, then taking that dimension to sample the next dimension, and so on and so forth. Now, what the researchers behind this paper, Parallel Wavenet, showed was that you can actually take a autoregressive distribution like Wavenet and actually distill it into a student Wavenet, which uses these transform distributions to go from just a set of noise vectors to a set of outputs that's the speech. So they show that you can actually distill this really complicated sampling procedure into this much more computationally efficient sampling procedure, which is pretty cool. OK, so the final family of models that we're going to talk about are these things called implicit latent variable models. You probably know them as GANs, but they're not just GANs. And the idea behind these is that you have, again, some latent variables that are generating these observed variables, but now instead of evaluating maximum likelihood, estimates, we're going to be learning a model that actually allows us to discriminate between data examples and generated examples. So as we saw before, these types of models that we looked at have these explicit likelihood functions. And often this has some parametric form, and that might be very limiting. So we might not want to parameterize our output distribution in terms of a Gaussian or some other parametric distribution. And so we might want to have a more flexible stochastic generation procedure. And so instead of actually using this explicit probability distribution, we're going to define an implicit probability density. So here we have the data distribution, which is this complex distribution here. And what we're going to do is assign some complicated density that doesn't necessarily have to be some combination of Gaussians or other parametric distributions. So we have this now hopefully more flexible stochastic generation procedure, which does not require this explicit likelihood evaluation like we had with the previous models. So one earlier form of these models was called generative stochastic networks, or GSNs. And the idea is basically just to use an autoencoder to successively encode and decode Monte Carlo samples. So sampling from in the data space, using an autoencoder to jump around in this space. And so this autoencoded jumping is only implicitly defined. There's no explicit form of the likelihood that you could write down. And yet, you can actually evaluate and train this model on MNIST digits and things like that. But another approach for parameterizing one of these implicit models, it takes this different approach with hypothesis testing. So what we're going to have is our data distribution here, which is in blue, and our models distribution, which is in purple here. And we're going to define the likelihood ratio. So as you might do in hypothesis testing, you evaluate what is the ratio of the likelihoods. And here we're going to say this is the probability of some observation that we would see given that the underlying distribution was actually from the data over the probability of this data example given that the underlying distribution was from the model. And so we can use Bayes' rule to rewrite this top and bottom. And then if we assume that there's equal likelihood of generating from each distribution, then what we'd have is the likelihood ratio here is expressed as this essentially discrimination task of can you discriminate one distribution from the other. So we have now this ratio of what is the probability given that it's of the data given this example, and what is the probability of the model given this example. So this is the main idea behind generative adversarial networks, or GANs. So in this type of framework, you have some latent variable z, which you sample from some usually fixed distribution like a Gaussian or a uniform distribution. You pass it through your generator model, which has some parameters. And that's going to directly output an example x. And that is defining this distribution p theta of x. But you can't actually write down that distribution. It's only implicitly defined by that generative mapping because it's directly outputting samples. Whereas we have our data distribution, which is still the same. And now what we're going to do is feed in examples from both distributions into a separate model called a discriminator, which is going to try to classify was this from the data distribution or not. So we have our generator and our discriminator here, which is just it's a binary classification. So it's what is the probability that it's the data for this example versus 1 minus that is 1 minus the model. And what we're going to do is try to evaluate what is the likelihood. So essentially evaluating what is the classification performance here. And so that's this expectation under the data distribution of the probability that it's the data, and then expectation of the model distribution of the probability that it's the model. And we can rewrite this using the discriminator in this form. And we can re-express this expectation as an expectation actually over z, and then we pass it through the generator. And so this is the objective here for generative adversarial networks, where you have a mini-max objective where you're trying to minimize this objective over your generator and maximize it over your discriminator. So you're trying to train your discriminator to classify between these two distributions as well as possible. And you're trying to train your generator simultaneously to essentially make these distributions as indistinguishable as possible. And so you're essentially trying to fool the discriminator into thinking that the generated samples are from the real data distribution. And so if you take this objective, you can actually analyze it and see that it results in generative models that minimize what's called the Jensen-Shannon divergence. So for a fixed generator, the optimal discriminator has this form. And I won't actually prove it, but it's just some math that gets you to that point. And so if you have a discriminator of this form and you plug that into the objective, then you can see that you would have these ratios in each of these log probabilities. And you can rewrite that as factoring out a factor of 1/2 from each of them. And now you have what is essentially a constant factor, and then the scaling factor, and then what's called the Jensen-Shannon divergence between the data distribution and the model distribution here. So you see that even though we motivated this from this like classification perspective, hypothesis testing, what we end up getting out is a kind of a different divergence measure. And so often people try to distinguish between these implicit models and these explicit models that we saw before. And people think about, you have this manifold of the data, which is some complicated shape in the data space. And an explicit model, which is often trained through maximum likelihood estimation, is often trying to fit essentially as much of the data distribution as possible. It's trying to fit this large, noisy curve to this entire manifold. Whereas these implicit models have this tendency to actually just pick up on certain components of the manifold itself rather than exploring the entire manifold. So this is generally referred to as mode collapse, where you'll see that these implicit models can generate very plausible generated samples, but often they aren't exploring the entire space of the data distribution, but rather focusing just on certain aspects of it. And in practice, these models tend to be difficult to optimize, much more so than the previous models that we saw. All of those tend to be fairly straightforward to optimize. But in GANs, you can end up with these varying kind of situations where, because you have this dual optimization problem, you end up with cases where it just doesn't converge to a good solution, essentially. And likewise, another issue with things like GANs is that it's actually very difficult to evaluate the likelihood of a given example under the model. So what people will often resort to are things like inception score, where you take a pre-trained inception V3 models. It's just a model for classification. And what you'll do is evaluate this quantity here, which is just essentially saying that I want for each data example to have a very peaked distribution over the classification. So I want these data examples to essentially look very much like real things. And I also want to have a broad distribution over all of the data examples of the things that I'm generally generating. So it's just kind of trading off between both precision and then this kind of dispersion over the entire data distribution. So I guess the main, or one of the most powerful or popular approaches that have been developed after the GAN is this thing called the Wasserstein GAN, or WGAN. And the basic idea behind it is just that the Jensen-Shannon divergence can be discontinuous and can result in cases where it's very difficult to optimize. Whereas if you take this different divergence measure, this Wasserstein metric, then that can lead to a much more stable and smooth training procedure. So the idea is just to evaluate this Wasserstein distance. And let's walk through this for very briefly, 1 second. What we're saying is that over all kind of orderings or pairings of data and generation, we want to find the one that has this Wasserstein distance, which is essentially the optimal distance you would have to move in moving samples from one distribution to the other distribution, which is generally referred to as optimal transport. So think of it as just the minimum cost of transporting points between these two distributions. And in practice, you can't actually evaluate this expression exactly. So people will evaluate this kind of approximation to it, where you restrict the discriminator to be of a certain type of class of functions, which are called Lipschitz, which just means that they have a bounded derivative. So they have kind of, they're smooth enough. And generally, this is enforced through either weight clipping or some type of gradient penalty. More recently, people have shown that spectral normalization of the discriminator's weights can result in much better performance. So if you're interested in GANs, like this would be a good place to jump in. With GANs, we saw that we had this latent variable, but we weren't actually inferring a latent variable for any given data example. And so we might ask, can we actually infer a latent representation? And indeed, people have looked at this recently, where you're actually simultaneously learning to generate, but also learning to infer a latent variable as well. So you can use GANs for things like semi-supervised classification and things like that as well. And some applications people have looked at, not just generating or not just transforming noise into observations, but also transforming between different forms of data. So here you have taking a map and transforming it into kind of the non-satellite version, or like a masked version versus generating the actual image, sketches to real images. People have looked at changing zebras into horses and back again, which somehow is a very exciting thing. And then people have also used GANs for things like I talked about, generating particle physics results, so trying to simulate actual experiments, and also looking at interpretable latent representations, synthesizing music, and even transforming between text and images. Yeah?
I'm not sure if you went deeply into this, but for the experimental simulation,
Mm-hmm.
I'm wondering if you start with the same data, does this method, why does this method improve the results, right?
So hopefully it should allow you to kind of interpolate between values that you might have observed, but you didn't actually observe. So that would be the hope, at least. It's not to say that this would necessarily always help, but there are cases in which maybe you have some type of simpler data, and you can use that simpler data that you can generate very easily to, with a GAN, transform it into something that looks like your more complex data and can actually help with supervised tasks. So progress in this area has improved quite a bit over the last 4 years, 5 years. And people are just astounded by the types of images you can generate these days. Yeah, it's pretty cool. So in the final kind of closing of the lecture, I want to briefly discuss kind of some broader topics. So we had these 4 families of generative models, and each had their benefits, some drawbacks. They all have these different kind of flavors to them. And even though I presented the models as totally separate or distinct ideas, a lot of work goes into actually combining these in pretty cool ways. So as we talked about, we have this idea of distilling an autoregressive model into one of these invertible models. Likewise, you can combine an autoregressive model with a latent variable model where you have this encoder, decoder, VAE style architecture, but instead of just generating at the output a Gaussian, you're generating kind of the seed to a autoregressive distribution, which would generate the individual dimensions of your observation. Likewise, you can combine these implicit models with explicit latent variable models, where your implicit model is actually forming this distribution in the latent space and allowing you to kind of come up with a more complicated posterior distribution. And another thing people have tried is actually having these explicit latent variable models with these invertible models down here as well. So you can kind of generate into a simpler space, but then evaluate your data in that space as well. So again, why do we care about generative models? We can generate and simulate data. So we saw that that might be helpful for certain cases. And we can also automatically extract structure from data. So these are kind of the main two reasons that people are excited. And there's a lot of work that goes in these days into developing better generative models. But there's because of all this work, the state of the art has improved so much that there's now starting to be some of these ethical concerns about if we have this data out there that we can very easily generate, and it's even fooling humans, that might raise some concerns because this is kind of a lot of power in the hands of potentially bad people. So all of these images are not real people, of not real people. So this is from this paper that recently we released called StyleGAN, where you can generate different looking people, different ages, different poses, lighting conditions, you name it. And so it's kind of like, these images are becoming so good that if you looked at any one of these images, you wouldn't really be able to tell if that was a real person or not. And so that might have some ethical implications. And as we talked about, text generation has become so good these days that at least for simpler kinds of things like these types of excerpts, it might be concerning if this was in the wrong hands. So it's definitely something to be aware of and think about. Hopefully there'll be more discussion around this, and it's just kind of picking up. So as we look forward, I think that we're going to see generative models applied to a lot more types of data. You can think of applying it to areas of science generally, but also generating art. I think it's only a matter of time before we have kind of automatic playlists that are generated on the spot for us based on our music preferences, things like that. It could be a very exciting time. And another thing people are really excited about is this idea of using generative models for model-based reinforcement learning, where you're actually using this generative model to plan out actions because it's clear that people are able to form these types of generative models and actually estimate what the future consequences of their actions will be. So this will be hopefully an exciting area of research over the next many years. And that's all we have. All right. Any questions? Any questions? We have a question.
Yeah, I remember reading about one of those pictures that was generated last year, and it took many, many hours, days to generate it.
Yeah.
Can you give me a sense, for the amount of computer time
So
you cycle through this?
So I don't know. So I guess it depends on if it's an autoregressive model, it's going to take a long time to generate if it's an autoregressive model, it's going to take a long time to generate each individual example. But generally, you're looking at maybe seconds, I would say, not much longer than that. Not for these high-resolution images. Yeah, you're going to be looking. I don't know exactly offhand, but these models are actually generated by GANs, not by autoregressive models. So I think more of the issue comes with the training. So actually, to fit large images and large models on GPUs is very difficult because GPUs only have a limited memory capacity. So in practice, what all these companies do is they string together, hundreds of GPUs potentially, and each GPU will be looking at one or just a handful of images, and then they train with these large batches in order to actually get good gradient estimates. So I don't know offhand, but I think you're looking at order of weeks or order of a week to train a good model like this, but that's on a large farm of GPUs. Yeah.
I guess within the discussion of parameter estimation and latent variable estimation,
yep.
I know, like in a lot of science contexts, you might be concerned with model parameter estimation. And I know, I guess there are some versions of like GANs that you can kind of like concatenate your standard normal with like conditional parameters. But I guess generally speaking, the errors that you can infer on those parameters is also something important, and interpretability, I guess, is important there too. So I guess my question is just, has there been any like work, I guess, on error interpretability in those contexts?
So in the context of parameter estimation, or in the context of generation, or
in like latent variable estimation?
Yeah, I don't know offhand. Oftentimes, I think there's a distinction between models that people will come up with in science for trying to explain their observations versus these types of models, which are very much just parameterized by deep networks. The latent variables can be whatever they want to be. So I think the deep learning community doesn't tend to focus on interpretability as much, although there is still a subset of people within machine learning that do care about parameter estimation and latent variable estimates. Yeah. Yep.
In that similar vein with the latent variable models,
yeah.
I was a little confused about whether, were you suggesting the generative model would be a deep network? Or
yes, yeah. So the generative model and if you have an inference model, that inference model, both of those are deep networks in that context.
But the latent variables themselves might still be a parametric, like a Gaussian, but then the mean and standard deviation would be functions sampled from this generating model. Is that right?
So yeah, so specifically, like in the context of variational autoencoders here, you have this Q of z given x, so that's going to be oftentimes a parametric distribution. Like 90 times out of 100, it's going to be a Gaussian distribution. You're going to sample a variable, sample an estimate, sample z from that. So you're sampling from this distribution and then passing that through your generator, which is parameterized by a deep network. And then the output here is itself another distribution. So this is going to be z, and then that's going to output perhaps a mean and a variance in the data space.
Wasn't Q supposed to be the approximation, like a smaller family to approximate the truth?
Yeah. So in practice, what you would actually want to do if you were trying to evaluate the true posterior would be to integrate over the prior to actually evaluate this true posterior distribution, which in general is not going to have a nice analytical form. So this approximate posterior here is just, it's restricted to be Gaussians oftentimes, and then you just find the best Gaussian you can for whatever data example you're dealing with.
And so then again, the inference model is another deep network
that
is generating parameters of these. This is like a mean field Gaussian thing.
Yes.
They're all independent, right?
Yes. Yeah. So the inference model here is generating perhaps a mean and a variance for Q, and then the generative model here is generating a mean and a variance, or just a mean for a Bernoulli distribution for this likelihood, this conditional likelihood down here. So each of these networks is outputting not just one thing, but potentially multiple things. Yeah.
Could you help me clarify the difference again between like explicit and implicit?
Yeah. So.
Like, is implicit just like you can like see the outcomes of this distribution, but you can't really tell what
So yeah. So an explicit distribution has a form that you can write down, essentially. So you can say that P of x here is a distribution that's defined by my model, and even though it has some latent variables, I can explicitly write out what the form of that distribution actually is. And even for a variational autoencoder, even though it would be really laborious to write down every single possible output for a given data example, I can still define the likelihood in terms of these explicit functions. So I have this kind of exponential family distribution that I'm dealing with, like a Gaussian distribution, that I can actually write down. Whereas in the case of these implicit latent variable models, like here, you're not outputting, so the generator here is not outputting a distribution over x, it's outputting a sample of x. So the idea is just that you no longer are able to write down explicitly what the likelihood function is for this model, because it's just defined in terms of the stochastic mapping from, or the mapping from z to x.
But if you had 100 for loops and you tried all possible z's, would you then get the distribution of x? Over
Yes, but you wouldn't be able to write it down in an explicit form.
okay.
Yeah. So even though we have this nice form for p of z, we don't actually have a form for p of x. Like we would never be able to actually write that down. We would just be able to kind of sample from it.
So is that just because it's a function of a random variable that you don't know how to analyze?
Yes. Yeah.
The only way you could write that down is if you sum over all possible z's, and that's not a compact formula.
Yeah.
It's defined directly. It's defined directly by the sampling procedure. Therefore, the joint probability distribution, the only way you could write it down is the sum over. It's literally write it as exponential or infinite sum over all possible z's.
But even then, you wouldn't be able, you wouldn't have a form for p of x given z. You just have the x.
So if there were just countably many z's, maybe you could get it.
No, even if you had countably many z's, because the point is that because your generator is not outputting a distribution, it's outputting a variable or a sample directly. You